Yeah, okay, thanks. And I will present StaTI, protecting against fault attacks using stable threshold implementations. And this work is co-authored by Simon Doge and Artemi Orcheniko. And in this work, as the name calls, we present the countermeasure against fault attacks, which is based on threshold implementations, which means it's also countermeasures against side channel analysis. So that being said, I'm going to start with, of course, physical attacks. And first category is the passive attacks, and this is well-known side channel analysis. In side channel analysis, the adversary is exploiting the observable leakage arising from the implementations, such as timing or power consumption of the implementation. And masking is the most well-known countermeasure against side channel analysis. And in masking, the secret data is split into number of shares, which are statistically independent from each other. So what happens is, if an adversary observes all but one shares of the implementation, then they get no information regarding the secret input. And the second category of the physical attacks is the active kind of attacks. And this is well-known fault attacks. In fault attacks, unlike side channel analysis, the adversary is intentionally disrupting the computations by injecting faults to the computations using some physical fault injection mechanisms, such as clock voltage glitching, EM waves, or laser. And we have redundancy as one of the most well-known countermeasures against fault attacks. In redundancy, what we do is we check if there is a fault injected to the computation or not. And if there is a fault detected, then we render the output as unexploitable by the adversary. So we can suppress it, or we can infect it so that it's random and it can't be used anymore. And the next widely used countermeasure is redundancy combined with masking. So this is good because in addition to fault attacks, it's also protecting against side channel analysis. And when we move on to the attacks, so we can categorize them in two main categories. And one is that exploiting wrong ciphertext. And here we are safe because we have redundancy. And if the output is wrong, then we can easily see it, and then we can render it as unexploitable. But the second category is the ones that exploiting data-dependent fault propagation. And here what happens is sometimes the fault does not propagate to the output. And also this propagation is dependent on the secret input. So if it doesn't propagate to the output, then we can't really detect if there's a fault injected or not. And since it's independent on the secret input, then it's going to reveal some information about the circuit. And now let's see data-dependent fault propagation on a simple example. And we have the AND gate here. This is a truth table of AND gate. And we have a fault injected to Y, and it's in the form of bit flip. So we just flip the value of Y. Since one of the inputs is changed, the output is also changed. But we see that the output is changed for only the half of the cases. And when we go back to X, we see that the output is changed when X is 1. So now we know that if the output is faulty, then X is 1. If the output is not faulty, then we know X is 0. So we call this kind of faults as ineffective faults because they don't always propagate to the output, and their propagation is dependent on the secret information. And there are some ways to protect against this kind of faults. One is to error check all the critical values in the circuit. For example, if we take this example, we can check the correctness of X and Y. And if we detect any fault injected to X and Y, then we can abort, or we can protect against this kind of faults. And the second one is we can ensure the fault propagation. So how we can see it here is there is a fault injected to Y, and now for all 4 cases, we're going to make sure that this fault is propagated to the output. And in this work, we go with the second option, and we propose StaTI, which extends threshold implementations using linear encoding with a single error check at the end. And before we go deeper into the countermeasure, first, I'm going to show you the adversary and security models related to the countermeasure so we know what we are protecting against and what we promise. And first, we assume the probing model to capture the side channel analysis adversary and to capture the physical effects of the glitches in the hardware devices. We also extend this model to glitch-extended robust probing model. And to capture the capabilities of a faulting adversary, we assume K gate register faulting model. In this model, an adversary can replace the outputs of total of K gates or registers in the circuit in the form of reset, set, or flip faults. And a reset fault changes the value to 0, a set fault changes the value to 1, and flip fault just flips the value of the targeted value. And in this work, we specifically assume first-order probing and first-order gate register faulting security, which means the adversary can observe only one wire in the whole circuit, or they can change the output of one register or one gate. And what we promise as the security is the probed intermediate value is independent of any secret variable. And then we also require the circuit to be correct and private. And correctness means the circuit is going to either abort or it will always give the correct output, so no wrong outputs. And the abort signal does not depend on the secret value. So this means the circuit is private. And now let's see what we use as masking and the encoding in StaTI. So we make use of Boolean masking. We take X in the binary field extension, and then we split it into a number of shares. Then the summation of those shares give back X to us. And specifically, we are using threshold implementations, which splits the computation into a coordinate functions, where each coordinate function calculates one output bit. And for the encoding, we make use of binary linear codes. And specifically, we make use of systematic code, where we take a code word, and then it consists of data, and together with the parity bits. And here we use the matrix P, and we are going to see it later in the presentation. P is the matrix that we use to compute the parity bits. And then what we call correct encoding is a code word in the linear code. So if there is a code word that is incorrect, it means it doesn't exist in the linear code we are using. And another notation we make use of is H, which is the parity check matrix. So if we multiply H with a code word, then it should give 0 if the code word is a valid encoding. And in this work, we specifically first share the input, and then we encode it. For example, if we use duplication, then we duplicate all the shares of the secret input. And now let's move on to properties of the countermeasure. First, we have correctness, non-completeness, and uniformity. And these are coming from the well-known threshold implementations. Correctness means we get the correct output when we give the input that we want. And non-completeness means each of the functions we see are independent of the secret input. And uniformity means if the input is uniform, which means we have a uniform sharing for a fixed input, the output is also uniform. So here, there's nothing new. These all come from threshold implementations. And these are all good to start, but we need some more properties to protect against fault attacks, because we know that threshold implementations is not secure against fault attacks. And it has been shown in many research papers. And the first thing we propose is fault non-completeness. And it means no gate is shared between two coordinate functions. And this is going to ensure that any single gate fault injected to one of the coordinate functions is going to affect only a single output bit. And it's not going to depend on any secret input, because we know that each coordinate function is independent of the secret input. So is this enough to protect against fault attacks? No, because the faulty output might be the input of the next function. Then we need to deal with that as well. And for that, we propose the notion stability. Stability states that any incorrect input code word of a shared and encoded register to register function is mapped to an incorrect output code word. And then we have the following theorem. The serial composition of correct, non-complete, uniform, fault non-complete, and stable shared functions is secure against a single probing adversary and a single gate register faulting adversary in a non-combined attack scenario. So the probing part is quite easy, because we are using threshold implementations, and correctness, non-completeness, and uniformity are enough to protect against probing adversary. And what we have next is imagine this is our function. We have coordinate functions here. And we inject a gatefold, a single gatefold. And then this is going to affect only one single output bit. If this is the last function of the circuit, then it's quite easy to detect the fault, because the output is obviously incorrect. And if this is not the last function, then we have one more function after this faulty one. And what happens here is that we have incorrect input code word, and through the stability, we're going to have incorrect output code word. So this is going to be detected if the last function of the circuit. And now that we know the properties of the countermeasure, and let's start with XOR and AND gates, because they are the most basic operations in binary field. And they are fanning off two single output, which means they are unstable, because they might map two different inputs to a single output. And if the second input is faulty, then this means it's not propagated to the output. And let's see it in some examples. We have the XOR gate here. It just computes A plus 1. And first we duplicate it, which means A prime is equal to A, and B prime is equal to B, which means they are input code words, both input and the output. And now we inject a fault to A and B. Now it became incorrect input code word, because A plus 1 is not equal to A prime, and B plus 1 is not equal to B prime. And when we see the output, it's still A plus 1, because the ones cancel each other. And the output is still correct output code word, which means XOR gate is unstable. And here we can see that if there is a fault injected to A, either A or the duplicate one, or a fault injected to B, then we know that XOR gate is going to give still correct output code word. And let's look at the AND gate. Here we have an input A, and the second input is 0. Then we know that the output is already 0. We duplicate it again. And the input and output code words are still correct, because there is no fault injected. And now we inject a fault to A, which makes it A plus 1. A plus 1 is not equal to A prime, so this makes it incorrect input code word. When we look at the output, it's still 0, because one of the inputs is 0. And now this shows that the fault didn't propagate to the output, and it makes it unstable. And what we can say here is, if there is a fault injected to A, and if B is 0, then the fault is not going to propagate to the output. And it might happen same with the B case. So if there's a fault injected to B and A is 0, then it's not going to propagate. Then in this work, we take these unstable encodings of XOR and AND gates, and we provide stable encodings for them. And we just use the general conditions I stated in the previous slide. For XOR, we're going to add a fault term if there's a fault in A and if there's a fault in B, when happens both of them together. And for the AND gate, we're going to add a fault term when there's a fault in A and when B is 0, so that it's going to propagate, or when there's a fault in B and when A is 0. So we're going to make sure that the fault is going to be propagated to the output. And now we saw how to secure XOR and AND gates, but this really doesn't tell us how to secure the full circuit. And here we provide some general methodologies for arbitrary functions to see how we can make them stable. And the first method is to use error detection. So we have an encoding, which is a correct, non-complete, and uniform. And this is the encoding of the function f. First, we set a global check value r. And initially, this value is set to 0, which means there's no fault detected yet. And when we compute the function, then we also update r. So we use the h function here. We compute the error check by multiplying the h matrix with the input. And then we're going to get 0 if there's no fault in the input, so if this is the correct code word. And the output of this multiplication is going to be 1 if the input is an incorrect code word. And then if there's a fault injected to input, r is going to be updated to 1. And at the end of the circuit, we're going to check the value of r. And if it's non-zero, then we're going to be sure that there's a fault injected somewhere in the circuit, and we're going to abort. And the next method is interpolation. And we have a function which takes x and outputs y. And the encoding of that function can be stable if we use interpolation. And first, we list all the valid encodings for the input, and then we list all the valid output code words. And now we list all the incorrect input code words, and we choose a random incorrect output code word. And what we do is we map all the correct input code words to the correct output code words, because this is how the function behaves actually. And next, what we do is we map all the incorrect input code words to a random incorrect output code word. And now we know that this list is finite. So by using interpolation, we can find such a mapping which maps all the correct input code words to correct ones, and incorrect code words to a random incorrect output code word. And now in this part, we deal with some arbitrary functions. And in this part, we are going to deal with some specific T+1 threshold implementations. And first, we focus on the linear functions and consider an invertible function L, and P being the function that computes the parity bits. And then this following construction is the stable encoding of this invertible function L. And how we know it? If we write this equation, then we see that when we calculate the parity bits of the input, and when we add it to the x prime, which was already parity bits existent in the input, they're going to be equal to each other if there's no fault injected to the input. And next, we calculate the function on the input, and then we take the parity bits, which means Lx is the output of the function, and we take the parity bits, which is the desired functionality of the stable function. And we know that this whole construction is a permutation because L is invertible, so we can always go back from output to input. Then we know that this construction is also stable, besides being correct. And the extension of this construction to shared domain is quite easy. Since it's linear function, we just apply this function share by share. And for the invertible nonlinear functions, first we consider permutation f, and we take the uniform and non-complete sharing of this permutation. And we know that this is also a permutation. And then the following construction is the stable encoding of this function. And how we know it? Again, we write this equation similar to the linear function. First, we compute the parity bits of the input, and we add it to the parity bits of the input that was already there. So if there's no fault injected to the input code word, then they're going to cancel each other because they're equal to each other. And now what we do is we compute the function on the input, and then we take the parity bits, which is the desired functionality already. And we know that this construction is invertible because we can already find the inverse function. And then we know that this is also stable. Because if there's an output, and if we can go back to input, which means there's no incorrect input code word can be mapped to a correct output code word. So we saw that T+1 threshold implementations was quite easy to find stable encodings, but the two shared threshold permutations is not that easy, because if we want to work with two shared ones, then we can't really keep the same input and output bits, like the same number of them. So we need to do some more expansion and then XOR them, which is not stable actually. So in this work, we base on the reconsolidating first-order masking schemes. And in this work, they propose some uniform solutions over two shares, and they work over 2 cycles. And now we just take those solutions, and we need to make sure that both cycles are stable. And in this part, I will only show an example of the AND gate. So this is the AND gate solution provided in this paper. And how we can make it stable is we can take all the AND gates and the XOR gates in this like 2-share AND gate and replace them with the stable XOR and AND encodings that I showed earlier in the presentation. And the whole new encoding is now stable. And until now, we were dealing with like really small functions, like small invertible linear functions or nonlinear functions. And now we're going to see how we can encode the whole state of the cipher. And first, consider a 4x4 state, which is actually quite common, for example, in AES. And how we encode the state is we take one row, and compute the parity bits of each element in that row. And then we sum them together, and we get the parity bits corresponding to that row. And in this construction, we can already see that shift rows is free, because in shift rows, nothing is changing in the parity bits. And we can also say that mixed columns can be directly applied to PI. So with this construction, we can already get really good reduction in the area size by doing linear operations. And for the nonlinear operations, I can't say the same, because we need to still follow the same strategy that I showed in T+1 threshold implementations. So what we're going to do is we take the row, and then we apply the transformation on that whole row. So first we compute the parity bits. We compute the function of each state element. And then we compute the parity bits and take the existent parity bits to check if there's a fault injected or not. And then we compute the output and take the parity bits of the output. So there's no reduction in the size, actually. And now this was the theoretical part of the paper. And then in the practical part, we implemented StaTI to protect Keccak. And in this work, we implement Keccak version 1600 bits, and with 4 and 2 shares. And then we check the stability of the implementation, and we verified it using the MFI tool, and it's an open source tool for fault verification. And what we can easily see is there's no overhead in time when we compare those implementations to unencoded TI, and this is the first good thing. And second, for the area overhead, we take a single Keccak S-box implementation, and a Keccak S-box implementation applied to the whole state, and a full Keccak implementation. And we compare it with other protected implementations. And first, this is the table for single Keccak S-box. First, we have the protected Keccak using a countermeasure from Diamond, Johan Diamond. And then the other ones are, we have first unencoded TI with 4 shares and 2 shares. And both implementations are protected using StaTI with duplication and parity codes. And the first thing we see is the countermeasure from Johan Diamond makes use of 10 cycles, which is quite a lot. If you see the cycles we use in StaTI, is 1 for 4 share and 2 cycles for 2 share. But when we check the area cost, we don't really have any improvement. The only improvement is coming from the cycles. And the second, in this table, we see the single Keccak S-box applied to whole Keccak state. And here, the interesting thing we see is if we take the unencoded TI, and then if we protect it using StaTI with duplication, then we see that the state size is 12,800. But if we encode it with state-wide encoding technique, then we get 6,500 state size. And if you see it here, we don't really have a gain in the area because, as I said, in the state-wide encoding, it's particularly efficient in linear functions and also the state size, but not really efficient in nonlinear functions. And last here, we see the full Keccak implementation. First, we have the TI implementations of Keccak with 4 and 2 shares. And of course, they are not stable because they are not even encoded. And first, we duplicate both of them. For 4 shares, the simple duplication yields a stable encoding, which is already really nice because we didn't do anything extra. And this is coming from the permutation properties of Keccak. And next, we are duplicating the 2-shared Keccak implementation. But now this is not stable. So now the StaTI comes into the stage. And with the 2-shared, we have the StaTI implementation in the last row and the simple duplication in this row. And we can see that by applying StaTI with a little overhead in area, we can get a stable encoding. And to conclude, in this work, we provide property stability, which is serially composable. And next, we formally define the gate register faulting adversary, and we show how to protect against this kind of adversary. And then we provide stable encodings for XOR and AND gates, which are the cornerstones of cryptographic primitives. And then we provide general methodologies to transform an arbitrary unstable function to a stable one. And then we provide methodologies for stable T+1 and 2 shared threshold implementations. We also go over state-wide encodings, which is particularly useful in linear functions. And we also provide some evaluation results of the Keccak implementation protected using StaTI. And that was the end of it. Thank you.